Good morning, everyone. I saw most of you have submitted your assignment, like more than 90% of the student has submitted. But few of you have not submitted yet. Is there any, do you guys, whoever has not submitted, do you guys are facing any problem? Am I audible to everyone?
Yes, sir.
Not assignment 2, assignment 1. Assignment 1 due date is this Friday. Whoever has not submitted, do you guys, if you guys are facing any problem, tell me, because this assignment you have to do. So I need to know why you guys has not submitted. Whether you guys are facing any problem in solving this, or any other reason that you guys joined late or anything, you guys need to tell me. I don't want to tell the names who has not submitted, but solution of I have already given you the solution of tutorial 1. I've already gave you the answers and discussed the problems with you. But what else you need for tutorial 1? Assignment 1 will discuss on solution of assignment 1. Will discuss this in this tutorial this Thursday.
Good morning, sir.
Yeah, morning. Most of the questions are very easy in the assignment. But still, if you I have not checked all the answers here, so I'll check, and if I find there's some mistakes or any problem, I'll discuss with you on Thursday. Or if you guys have any questions also regarding the assignment, particularly, I think many of you faced problem with question 5. So maybe I'll discuss with you guys on this Thursday, this question 5. Um, yes, so whoever has not submitted, is there any reason you guys need to tell me? You, I'm giving you some time. You tell me by tomorrow by email, okay? You need to tell me by tomorrow some email. You need to send me that why you have not submitted this. If you guys are facing problem, if you don't tell me, then you will be in trouble, okay? Because you have to face these questions in the mid sem, end sem. So
Sir, I have problem in question 5.
question 5, I told you we'll discuss on Thursday.
Okay, sir.
If this is, I told you that you can submit partially this assignment also. Like if you could solve 3 or 4 of the problem, that is fine. You submit assignment with 4 of the solution. Okay, so another thing is that I'll take a quiz on next Monday. Next Monday means this 9th September. I'll take a quiz on this unit 1 up to this Lagrangian. This Lagrangian formulation, I'll take a exam quiz. It will be, I'll give you 3 or 4 questions and you will have 20 minutes to solve the questions. Okay. And you guys bring some A4 sheet and then you solve on the A4 sheet and then upload. Okay. I'll give you total half an hour to solve and upload.
This chapter, this motion of system particle.
No, not up to this Lagrangian formulation. This equation of motion. Whatever we have derived so far. For example, in the last class, I gave you many example of this simple pendulum, and this free particle, how to set up the Lagrangian and solve the Lagrangian equation of motion. Up to this much, I'll take quiz. There will be three. I'm not sure. There will be either 3 or 4 questions, and you have to solve all of them. So there will be no optional. So the okay. So I'll take a quiz. This will be quiz 1. This will be on 9th September. And you will have 3 or 4 questions. I'm not sure. Yes. Okay, so this pen is not working. Wait for a minute. Let me see. Yeah. So there will be 3 or 4 questions. I'm not sure. 3 or 4 questions.
Yes.
And you will have 20 minutes to solve these 4 questions. And you have to upload by like this Monday. So this exam will start at 10 a.m. and you have to solve and then upload by 10:25. Okay, and then we'll have the regular class as usual after this quiz. Yeah, and this will be up to this Lagrangian formulation, up to Lagrange's equation of motion, up to Lagrange's equation of motion. That means up to this last class. When this last class happened, this was up to this 30th August. Okay, up to this class. Yeah. Okay, another thing is that whether do you guys have any problem regarding how to set up the Lagrangian and then its solution? Do you guys want more example of this, how to set up the Lagrangian and solve these equations? Last day, at the end, I speed up a little bit on this free particle solution for this plane polar coordinate. Yes, lecture 2, what is the problem? Lecture 2, what doubt you have? I don't remember. You have to tell me. This way I cannot continue this way. I don't remember what I discussed at the lecture 2 happened, I think 10-15 days back. I don't remember what example I discussed at the end. Okay, so let's continue. So, do you guys have trouble on the finding solution for this plane polar coordinate for the free particle? I speed up a little bit.
Yes, sir.
This quiz, these marks will be added to the final grading. This is not for self practice. We'll count the marks towards your grading, and it has 10% of your total grading. So it's not optional. Okay. Any problem regarding this free particle solution? If you have trouble, tell me. Or if not, then I'll show you one more example, and then I'll move on. Okay, it seems no one has any problem. So okay, so I'll give you one final example of this. One is that particle moving in a central force. This is the final example I'll show. I also included some problem of how to set up the Lagrangian in your in your next tutorial as well. Tutorial as well as in the assignment also. So you in next assignment I'll give you some problem to set for on this. That's how to set up the Lagrangian and then derive the equation of motion. Okay, so let me show you one more example. This particle moving in a central force. Okay. So central force is basically means a force which is directed inward or outward. For example, let's say you have this point and the particle is moving around this point. Okay. For example, all this planetary motion, like movement of Earth around Sun, and all this planetary motion, they are also example of central force problem. That if you have a particle moving around a certain point, and if this force is directed either inward, it can be inward, it can be inward, can be outward as well. Okay, but the important thing is that it depends on the distance between these two particles. It depends on this radial distance r between these two particles, and then it's generally called a central force problem. In classical mechanics, this movement of this planetary objects, that is a very important topic. But in your syllabus, it's not there. So we'll not discuss. But the central force problem is somewhat similar to this planetary motion as well. So here, first we need to define the force. So generally, this central force, all these central force, they have R dependence. R means this distance between this center and the object of, let's say, this is mass m, which is moving around this particular point. So let's say here we'll consider a particular type of force, let's say F, which is given by this, let's say R square, where K is a constant. Okay, where K is a constant. And okay, and this is R dependence. That means this is attractive force. This is not repulsive. Force is minus K by R square. That means this force is also attractive force. Now we want to set up the Lagrangian for this particular type of force and particular type of movement. So how should we proceed? So firstly, how many degrees of freedom we have? Let's say this is a plane. Okay. this is not a three-dimensional space. This is only a plane. So this particle is moving on this plane. Then the number of degrees of freedom that we have in this case, that is 2. But what are the generalized coordinates that we should use in this problem? Whether we should use x, y, or r and theta in this case, can you guys tell me?
R and theta.
Yes, we should use
R and theta.
we should use r and theta. Now we need to set up the Lagrangian. So how we need to set up the Lagrangian. That means we need to know kinetic energy and potential energy. So if this is generalized coordinates r and theta, then what is the expression for kinetic energy in this r and theta coordinate? This we have discussed in the previous class, that if you have Cartesian coordinate system, then kinetic energy is given by half m x dot square plus y dot square. But in this plane polar coordinate, you can show this kinetic energy will be half m r dot square plus r square theta dot square. And I also told you to derive this in case of spherical polar coordinate. So you should do that as a homework. How to transform this equation kinetic energy from plane polar coordinate to this this kinetic energy from Cartesian coordinate to plane polar coordinate or spherical polar coordinate, how to convert them. So you should know. Now the important thing is that how to find the potential energy in this case. We know the kinetic energy in this form. Then how we'll find the potential energy? Can you guys tell me how we should find the potential energy in this case? Potential energy means what? Potential energy means work done by the force, right?
Plus dot dr.
Yes. So in this case, the force is given in this form. So we can find out the potential energy by F dot dr. But what will be the limit of integration in this case? This integration you have to do with some limit, right? So what will be the
0
limit
to
of
r.
integration?
Sir,
Yes?
0 to r. 0
No,
to r.
not 0 to r. This will be okay. This will be infinity to r. Okay. So it is
Sir,
like
y,
you are
sir, y
moving the
infinity.
object from infinity, and you are placing the object here at this point, and that is the total work done by this force. So this integration is from infinity to r, and then you can show this will be infinity to r. Sorry, this will be k by r square dr. And then you can show this integration will be minus k by r. If you have this limit, it will be k dot r. Then the Lagrangian will be t minus v, and t we know that t is given by half m r dot square plus r square theta dot square minus k by r. This is minus k by r, so this should be plus. This is plus k by r. Okay. Now we know that Lagrangian equation of motion del L del Qj dot minus del L del Qj, this is equal to 0. Now in this case we have two generalized coordinates, Qj's are r and theta. So we'll have two from here we'll have two equation of motion. So for one equation of motion will be d dt of del L del r dot minus del L del r equal to 0, and another equation of motion will be d dt of del L del theta dot minus del L del theta equal to 0. So we'll have two equation of motion. So we know this Lagrangian in this form. So we need to find these quantities del L del r dot, del L del r, del L del theta dot, and del L del theta. We have to find this. Okay, let me write this again. Half m r dot square plus r square theta dot square plus k by r. Now, what is this value? Del L del R dot. What will be the value for del L del R dot? This will be M R dot, right? This will be M R dot. This term there is no R dot dependent. And what will be the value of del L del R? This will be M R theta dot square. M R theta dot square, and this will be minus K by R square. This is del L del R. We also need to find del L del theta dot. What is del L del theta dot in this case? M R square theta dot. M R square theta dot. And del L del theta, this is equal to 0.
No.
So from this first equation, if you do for this equation for R, so for that we'll get d dt of EM R dot minus del L del R. That means EM R theta dot square plus K by R square equal to 0. So basically from here you are getting EM R dot minus EM R theta dot square plus K by R square. This is one equation of motion. This is, let's say, equation 1. And from here, this theta equation, you will get another equation. And that equation will be d dt of M R square theta dot minus 0. This will be equal to 0. Del L del theta is 0. So from here, you are getting twice M R R dot theta dot plus M R square theta double dot. This is equal to 0. This is equation 1 and 2. So this equation 1 and 2 here are the equation of motion. Equation of motion. Okay. So now instead of this particular form, if someone gives you any other form for the central force problem, so you can do this problem similarly. Okay. Either this way or you can find this way also. You can start from this equation, what we have done for the free particle, that this for in terms of this generalized coordinate, you find this generalized force QR and Q theta, what we have done for this free particle. That way also you can find out. So either you find this generalized force or you find the potential. So sometimes it will not be possible to directly derive the potential. Okay. So in that case, you have to use this definition of generalized force. This equation of Lagrange's equation of motion, this form of Lagrange's equation of motion, it depends that whether you can write this force that is acting on the particle in terms of some potential or not. For example, that whether you can write in this form or not, where V is the potential, in that form whether you can write or not. If you can write the force in that form, then you can use this form of equation. But like in case of the free particle, we showed you that there you cannot write in terms of some potential, because that there the force is not known. So if we don't know the exact force, then we can find the component of the force from this definition of generalized force. And then also we can solve, we can set up this equation of motion, Lagrange's equation of motion. Okay. So I don't want to show any more example. There are many problems you can do. If you read some books or if you search, then what is this? Kinetic energy expression in spherical polar coordinate. What happened? What is the problem? Kinetic energy expression in spherical polar coordinate. if you guys are using chat, okay, you guys need to tell me the exact what is the exact problem. I cannot read your mind. What you have, what doubt you have in the doubt you have. If you speak, it is much easier for me to understand. Okay, otherwise we waste lot of time.
Sir, I have sent the doubt in chat. Sir, image. Please check.
This we'll discuss on Thursday. This is long back. Okay, this will discuss what is the problem. This is simple surface integral, right? I told you many times that if you guys have any problem in the last tutorial also, that whether you guys have any more problem or not. Calculate the surface integral. Okay, we are on different topics. We will not discuss it now. We remind me this on Thursday. Okay. On Thursday, you remind me this problem.
Okay, sir.
Okay, so I don't know what problem you have on kinetic energy expression for spherical polar coordinate. I told you to transform kinetic energy expression from Cartesian coordinate to spherical polar coordinate. This I told you to do as a homework. Okay, I don't know what problem you have. Okay, so what I was telling you about this Lagrangian, if you read any books, you will see there are many problems set. Okay, so you guys should practice some of those problems. I have already included some in the tutorial. In next tutorial also, I will include some, and some in the assignment also. I'll include some a few more problems. Okay, but you guys should practice this or okay, and. Mm, last thing is that okay, if you guys don't have any other problem, we'll move on to next topic. So we'll try to set up this Hamilton's equation of motion. But before that, we need to give you some few definitions. Okay, we need to accustom to it few more nomenclature, few more definitions. So first definition is generalized momentum. So how do we define momentum? So how we have so far defined momentum of a particle? For example, let's say this is a Cartesian coordinate x, y, z, and you have some moving particle and some at time t, let's say its position is given by x, y, z. Okay. Or let's say some particle is moving along x-axis and at a given instant its position is at x. Then how we have defined momentum so far? What you need to know to define the momentum of this particle? Let's say for this particle, for the particle moving along x-axis.
Mass and velocity.
Mass into velocity, right? This is called linear momentum. There is also definition of angular momentum, that if this particle is rotating around some axis, then you can define angular momentum as well. But linear momentum, that is simply that if this particle mass is m, then you can say this is linear momentum is mv or m dx dt. So you can see this linear momentum, it depends on the coordinate in this particular coordinate system, which is moving along x direction. So this position coordinate position of the particle, it appears in this expression. Okay. Now we are now working in terms of the generalized coordinates. So now our coordinate systems are generalized coordinate. Okay. So we have moved away from this Cartesian or polar or spherical polar, all those type of coordinate system. So now we have a new definition of coordinate system, which is called generalized coordinate, and in which QJs are all are independent. So here, how do we define the momentum of the particle? Let's say you know this generalized coordinate of a particle. Then how you will define the momentum? Will it be simply m qj dot, or it will be some other quantity? For example of this, let's say in this case of simple pendulum. In case of simple pendulum, we know that theta is the generalized coordinate. So whether m theta dot, this will be the momentum in this case, or not? Can we
No.
write whether this has the dimension of momentum? This theta is simply an angle, right? So this is not typical of your momentum, that you cannot compare this momentum with your linear momentum. Like what you have known so far, that P equal to mv, this is not equivalent to m theta dot. Or in other cases, for example, in this case, that you have a mass, you have this mass attached to a spring. Okay, so in this case your generalized coordinate is x. So now if you write in this case momentum is simply mx dot, it looks similar to the your general normal linear momentum. But you can see that in this case of simple pendulum, here the generalized coordinate was theta, and here generalized coordinate is x, but the momentum definition looks very different. The dimension is very different. So we need to define a general momentum in a very generalized way, and that definition is this generalized momentum. Generalized momentum Pj, this is defined as del L del Qj dot. This is the definition of generalized momentum. Okay. You now you can go back to this a very simple problem. For example, of this free particle, and there you can see whether when you define this way momentum, in that case that was del L del x dot, whether that is equivalent to a momentum or not. But this is the definition of generalized momentum. So now on, whenever we'll talk about momentum of a particle, it will be generalized momentum, and it is defined by this quantity, that del L del Qj dot. Now these definitions are not very natural. Okay, so you need to get used to, need to write and remember this definitions. Okay, these are not very natural. For example, what will be the differentiation of Pj dot? In previously, if you do dp dt, this will be simply m d2x dt2, right? That was the p dot in case of linear momentum. But from Lagrange's equation of motion, you can find this expression for Pj dot. So in Lagrange's equation of motion, we know d dt of del L del Qj dot minus del L del Qj, that is equal to 0. That is Lagrange's equation of motion. So what you can say, that d dt of del L del Qj dot equal to del L del Qj. So this is nothing but the Pj dot that we have just defined, the del L del Qj dot, that is the generalized momentum. So you can say d dt of Pj, that is equal to del L del Qj, and that is Pj dot, right? This is Pj dot. Pj dot is del L del Qj. Okay. So I know this expression looks very unfamiliar to you. For example, I told you that definition of Pj, that is del L del Qj dot, but now we are getting Pj dot, that is equal to del L del Qj. That's why I told you that these are not very natural. That but we cannot do anything about this. You have to just remember that these are the definition of momentum and its derivative. Okay. Now we also have derived a very important relation here. So let me derive this again. That okay, let me formally tell you what is the definition. This is called cyclic coordinate. cyclic or ignorable coordinate. Cyclic or ignorable coordinate. Cyclic coordinate means that if Lagrangian is not function of a generalized coordinate qj, then that is called cyclic coordinate. That if L is not a function of a given generalized coordinate, qj, then qj is called cyclic. qj is called cyclic or generalized coordinate. Okay, so that means this will be 0. That means del L del qj will be 0 for given for that particular coordinate. Okay, it is not that it will be 0 always. For example, in this for example of the central force problem, I told you that you have two generalized coordinate r and theta. So if L is cyclic for r, then only del L del r will be 0. Or in case of, you can see this, in case of central force problem, del L del theta was 0. Del L del theta was 0, but del L del r was not 0. So del L del theta is 0 means L is cyclic for this coordinate, generalized coordinate theta. So in the central force problem, theta was cyclic in case of central force problem. Okay, and when that happens, that conjugate momentum. Okay, so this generalized momentum, this has another name also. This Pj, this is also called canonical momentum. Canonical momentum or conjugate momentum. Or conjugate momentum. So this Pj, this has various name. Either it's called generalized momentum, it is also called canonical momentum, it's also called conjugate momentum or momentum conjugate. Okay. Now when this particular coordinate is cyclic, then this momentum conjugate will be conserved. For example, let me derive this again. That let's say qj is cyclic. Qj is cyclic, okay. Then the Lagrange's equation of motion, this will be del L del qj dot minus del L del qj, this is 0. Or you can say d dt of pj dot minus del L is cyclic. That means del L del qj is 0. So you can say this is 0, that is equal to 0. So that means d dt of pj, that is equal to 0. Okay, so that means pj equal to constant, right? If some derivative is 0, then we can say pj is constant. So that's what, like, if qj is cyclic, then the momentum conjugate is constant. Then generalized momentum is conserved. This is a very important result, that if a coordinate is cyclic in the Lagrangian, then its corresponding generalized momentum is conserved. It's a conserved quantity. Okay, now we can also derive energy conservation from this. We can also derive energy conservation. So now let's go back to let's go back to the Lagrange's equation of motion again. So Lagrange's equation of motion, that d dt of del L del qj dot minus del L del qj, this is equal to 0. Or you can say del L del qj, this is equal to d dt of del L del Qj dot. Let's say this is equation 1. Now Lagrangian, this is the function of what? You can see from this expression. This Lagrange's is generally a function of, it depends on Qj, the generalized coordinate, its derivative, Qj dot, and sometimes it also depends on the time. This is the general form of the Lagrangian, or that Lagrangian function. Any Lagrangian function that will construct, you will see that you will always depend on these three particular variable. It depends on the generalized coordinate, its derivative, and the time. Okay. Now let's consider two things. Let's consider one, that the system is conservative. That system is conservative. This conservative system means it does this Lagrangian, it does not depend on velocity. That the potential energy is not depend on the velocity. V is not a function of velocity. And from here you can say del V del Qj dot, this is equal to 0. Okay. Now what you can say then? Then you can say del L del Qj dot. This you can write del L T minus V del Qj dot. L is basically T minus V. Okay. And if del V del Qj dot is 0 for conservative system, then you can say this is del T del Qj dot. And del L del Qj dot, this is basically Pj that we have just defined. This is generalized momentum. So in this case of conservative system, you can say that del T del Qj dot, this is also equivalent to the generalized momentum. Okay. This is first consideration, that system is conservative. And then you can say this particular relation, that generalized momentum, this you can also write in terms of del T del Qj dot. And second thing is that this constant do not depend on time. Okay. Constant do not depend on time. Constant do not depend on time means your Lagrangian will be a function of only Qj and Qj dot. Okay. Initially, I told you that Lagrangian, this is in general is a function of Qj, Qj dot, and time. But now we are considering that constant do not depend on time. So Lagrangian is just a function of Qj and Qj dot. And if that is the case, then you can write dl by dt. This is not explicitly a function of time. Okay. So then you can write dl dt. This is del L del Qj del Qj. Sorry, this will be dQj. dQj dt plus del L del Qj dot dQj dot dt. So what we have done, we have done partial derivative with respect to both Qj and Qj dot. This partial derivative we have done. Okay. Now what is del L del Qj? Del L del Qj is basically equal to d dt of del L del Qj dot, that we have derived here as equation 1. The del L del Qj, this is equal to d dt of del L del Qj dot. And if we replace this here, this del L del Qj, if we replace this by d dt of del L del Qj dot, we have just simply replaced this. Okay. And dQj dt, that is simply Qj dot. Plus we can write summation over del L del Qj dQj dot dt. Okay. This you can simply write summation over j d dt of Qj dot del L del Qj. This you can check. You can check whether you can write this or not. Okay. This you can check whether you can write from this expression to this. Okay. Now del L del Qj dot. This should be del L del Qj dot. This is also del Qj dot. This is not simply del L del Qj dot. Okay. Now del L del Qj dot, this is the definition of our Pj. So we can write from here, this is equal to Qj dot Pj. Oh God. Okay, let me share this again. What happened? Sorry, let me reconnect this, my iPad again. But now it's okay. So what we are getting here, ddt of Qj, and the left hand side is dl by dl dt. Left hand side is dl dt. So from here, what we can say that d dt of summation over j Qj dot Pj minus L, this is equal to 0. So this part is simple mathematical manipulation. Okay. So maybe if I'm doing it at a little bit higher speed, so it may be difficult for you to follow all this Qj and Qj dot. But if you do it yourself, it should be easy. You guys should be able to do this. Okay. We have done simply partial derivative, and then we have replaced del L del Qj by this definition, dt of del L del Qj dot. That's all we have done. Okay. So now if ddt of this quantity is 0, that means that this is a constant, right? So if this ddt of this quantity is 0, then this quantity Qj dot Pj minus L, this should be equal to not 0, this should be equal to, this should be a constant. Okay. And this is called Jacobi's integration. Sorry, this is called Jacobi's integral. Okay. Or this expression is also equal to the Hamiltonian. This expression, this is also equal to, expression is also called Hamiltonian. This expression is also called Hamiltonian. H equal to J Qj dot Pj minus L. This is also called Hamiltonian of the system. Okay. Now
Sir,
yes.
Sir, is it the same that we read in chemistry, the Hamiltonian?
Hamiltonian in chemistry. Where you have read Hamiltonian?
Sorry?
In quantum mechanics or some other area?
Yes, sir. Quantum mechanics.
Yes, in quantum mechanics also, this is not exactly equal, but this concept of Hamiltonian there also works. But that Hamiltonian is different. That Hamiltonian, that definition is different. Okay. But this formulation of Hamiltonian, this also works for quantum mechanics as well. Okay. That particular Hamiltonian was Hamiltonian is the total energy T plus V there also. But there we have arrived at that Hamiltonian from a different perspective. But here that is also total energy of the system. Here also total energy is, but the concept is same. But how we arrived at that particular expression for Hamiltonian, that is different in quantum mechanics. But the concept is same. Okay. That this
Okay,
formulation is same. And that is one of the benefit of using. So as you have seen that instead of Newtonian mechanics, we are doing much more complicated thing, but we are getting the similar equation of motion. So that's why if you ask why we're doing all this, why we're getting into all this trouble. So that is that this formulation of this classical mechanics, they are very versatile. They can work for a wide varieties of problem. For example, this Newtonian mechanics you cannot do in case of relativistic particle or in case of quantum mechanics. But now you can see this Hamiltonian, this you can simply apply to this quantum mechanics, or you will see this Lagrangian, those you can also apply in case of relativity. So those has much more wider application, and that is one of the advantage. And that's why we are getting into all this trouble of why of Lagrangian and Hamiltonian. Okay. So this is called Hamiltonian, and under certain circumstances, this will be equal to total energy. So Hamiltonian, this is, you can see this is constant here, but there will be under certain circumstances, few special circumstances, few special circumstances. So the first thing is that this coordinate transformation, this Ri, this does not involve time. It only depends on Qj. Does not involve time. Does not involve time. And second thing is that potential is not velocity dependent. That V is not a function of Qj dot, not a function of Qj dot. Then only you can say that this function, this Pj, Qj dot Pj, this is equal to total energy. Then you can say this H, this is equal to T plus V, this is equal to total energy of the system. And that will be then conserved. Only for, will not go into how, why we are making this particular cases. So, okay, but only for this few special cases, then only this Hamiltonian will be total energy, and that will be conserved. Okay, but I wanted to show you this this particular expression, that H, this is equal to J Uj dot Pj minus L. This is Hamiltonian. This is the very important quantity. And from this, we'll go move on to the next, how to formulate the Hamiltonian mechanics. Okay. And then I'll show a few one or two examples. And that will be end of unit 1. How to solution of this Hamiltonian Hamiltonian equation of motion. Derivation of equation of motion using Hamiltonian formalism. Okay. So we will end here this class. In next class, I'll give you examples of how to determine Hamiltonian equation of motion. Okay. So yeah, do you guys have any question? What is this?
Sir, in that which the constraints do not depend on time, sir, that topic, sir. Sir, what kind of constraints are you talking about?
Constant, you tell me. We have defined this constant, various type of constant. Do you remember this holonomic constant, non-holonomic constant, rheonomic constant? Those lectures. There we have categorized that there will be two type of constant. One will be sleronomic constant, which do not depend on time, and rheonomic constant, which depends on time. For example, I told you that if you have a rigid body, then the distance between two particles is constant, right? And these
Yes,
constants do
sir.
not depend on time. Okay.
Yes,
So those cases. So wherever you will see the constant equation does not involve time, so this will be applicable to those cases.
and sir, below that, sir, in that expression of dl by dt, sir, how did you move from the first step to the second step, sir?
Here to here.
Yes, sir. This one.
This is I replace this del L del Qj by this expression, and this expression comes from here. That del L del Qj, this is comes from Lagrangian equation. That del L del Qj equal to ddt of del L del Qj dot. And I just replace del L del Qj by this ddt of del L del Qj dot. And dQj dt is dQj dot.
Okay.
Okay. This is simple mathematics. If you do once at home, then you should be good. Any other question? Okay, if not, then okay, let me stop sharing this. And then okay, then let's end the class here today. And remember, we'll have exam on Monday. Okay, okay, then let's stop here. We'll see tomorrow again. Okay, bye bye.
Thank you, sir.